Okay, so the last few of these kind of evolutionary models, I'm just going to kind of just go through. I'm not going to create the spreadsheets from scratch because they're quite complex, but I'll just kind of go through what we're doing and, just relate the spreadsheet to the model. Okay, so we have a situation here where we have different parts of the factory, and each of these have a certain demand for tools. So we have the fabrication, which is at x coordinate 1 and y coordinate 4, and there's a demand 12. We have the painting, which is at 1 and 2, and has demand of 24. Now, the idea is we want to put out our tools somewhere to basically minimize the combination of distance and demand. So we want to minimize the average distance to each of these areas of the factory weighted by demand. So it's more important that we're closer to the paint because the demand is 24. And to do this, we basically just minimize the demand. So here we've got the demand for fabrication. Then the distance. So here this is the x distance, x minus 1 plus y minus 4. And then we have, for the paint, we have a demand of 24, and the distance is x minus 1 plus y minus 2. And then we have a distance of demand of 13 and minus 2.5 and 2, which is the area of the sub-assembly. Okay, so let's just go back to the painting place. This is at x equals 1 and y equals 2. And what we're doing here is we're finding the difference between our tool bin location and the x variable. So if it's 5 minus 1, it would be 4. And the difference between the y location of the tool bin and the y variable for the paint, which is 2. Now, let's just I put together this. So say, for example, we've got our paint location at 1, 2, and our tool bin at 3, 3. What we're calculating here, these absolute values, is the distance here using this scheme would be 2. So we're going from 1, 2 to 3, 2, and that would be of length 2. And the distance from the vertical would be of length 1. So we basically add up the difference horizontal and the difference vertical, the difference in the x and the difference in the y. So we have a length of 3. And here we have, this is if we'd done what we'd done in the previous chapter and used Euclidean distance. And then basically it's just the hypotenuse. So it's like we square this difference, we square that difference, we add them together and we square root. So if we'd been using the Euclidean distance, it would be 2 squared 4 plus 1 squared 1 is 5, so it would be the square root of 5. But here it's just 2 and 1 is 3. So again, imagine that our tool bin was at 3, 3. 3 minus 1 is 2. 3 minus 2 is 1. Total distance is 3. So what we're doing here is we have the tool bin location, and we basically have this formula here. The absolute difference from here is the fabrication plant, which is at 1, 4. So it's the difference in the x coordinates with the tool location B15 plus the difference in the y coordinates multiplied by the weighting of the demand. And we use the dollar here because we're dropping down. So the next one is for the paint. Again, it's the difference between 1 and 3 and 2 and 3. And we're multiplying it by, which is 2 plus 1 is 3. Multiply the demand of 24, and we get 3 times 24 is 72. Down there. So then basically we sum all of these distance times demand variables, and we basically set this tool bin location to minimize this value. So let's go to Solver, and let's just kind of start off from scratch. So we're going to minimize B23. by setting these variables here. And subject to constraints, we know that we're not getting any bigger than 5 variable. We're not going to bother having any negative x coordinates and y coordinates because everything is going to be positive. It wouldn't make any sense for the tool bin location to be negative because that would create huge distances. So let's just say that our tool bin can be anywhere between 0, 0 and 5, 5. So we set these guys are greater or equal to 0, and they're also less than or equal to 5. So those are my constraints. Again, we're going to use this is because we have the absolute value um, in the optimization function. We actually have to use the evolutionary solver because it's not a smooth linear or quadratic function. Click solve. Oh, there we go. C15, not C1515. And I'll just stop while we... Okay, and this is the final solution. Funnily enough, this is actually a little bit better than the one in the book. So we have our tool bin at around 2.5 on the X and 2 on the Y. It didn't quite make it. Let's just make it 2.5 and 2 to be simpler. And then we get a much better. And that's the thing with this evolutionary solver. It doesn't get you a perfect solution always. It can sometimes get stuck close to the actual solution. Now, this is not easy, particularly imagine if we had a factory with like 50 locations and a more complicated problem, this would be difficult. One thing to do would be to actually use the squared distances rather than absolute distances. Then we could use the standard nonlinear solver and everything would be a lot more efficient and a lot quicker. But here we are, the model with the absolute value.